Hi, I'm Joe Nash. Today I'll be presenting BinRec, Dynamic Binary Lifting and Recompilation. I would like to thank all my co-authors, especially my co-first authors Anil, Altinay, and Taddeus Kroes. It is fun to write new software, but the fact of the matter is there are many legacy binaries being used today. The downside of legacy software is it does not have the benefit of recent improvements in algorithms, toolchains, best practices, or use patterns. A famous example of rewriting a legacy binary is when Microsoft patched a buffer overflow in their equation editor. They did a surgical binary patch where they inserted a bounds check by hand. In addition to patching, practitioners like to reverse engineer, re-optimize, or harden binaries for security. In all these cases, they're faced with a fundamental challenge: analyzing the binary. We identified 5 core analysis challenges for static binary rewriting. These challenges are code and data separation, indirect control flow resolution, ill-formed code, obfuscation, and external entry points. Some of these challenges are undecidable, some are merely extremely difficult, but in either case, static rewriters turn to heuristics. The use of heuristics means the approaches are tuned to work for a particular use case and cannot be relied on in general. Beyond the theoretical challenges, many static binary rewriters have practical barriers to their adoption. They produce rewritten binaries with poor performance, especially when adding instrumentation. In addition, they often use ad hoc program representations that require re-implementation of textbook analyses and transformations. The existing binary recompilation frameworks do static analysis, and they are not able to rewrite standard benchmarks. Mixema is an actively developed static binary rewriting framework. I'd like to thank the developers of Mixema for making a fine tool which is easy enough to use that we can do an evaluation on it. However, it cannot correctly recompile a majority of benchmarks in the Spec 2006 integer suite. In contrast, our tool, BinRec, can correctly recompile every benchmark and outperforms current approaches. Dynamic analysis provides us a way to overcome the limitations of static binary rewriting. To that end, we created BinRec. BinRec takes dynamic traces through a binary and lifts them into LLVM-IR by building off of the S2E project. We produce a well-formed LLVM-IR module and enable the application of off-the-shelf LLVM optimizations and transformations like SafeStack and Address Sanitizer. We used BinRec to successfully recompile the entire Spec 2006 integer benchmark suite without heuristics. Finally, BinRec produces faster rewritten binaries than existing tools, with about 29% overhead relative to optimized input binaries. Now I'd like to discuss how BinRec overcomes the limitations of static rewriting. The code versus data separation challenge is well known in binary analysis literature, so for the sake of time, I'll just discuss how we address it. There can be read-only data in the code segment, so as prior work does, we keep a copy of that segment in the rewritten binary. Instead of using heuristics, we dynamically observe whether a value is used to set the instruction pointer, and therefore is code. Our disassembly is based on the actual executed control flow, so we never accidentally disassemble data regions as code. I will illustrate a challenging example to rewrite in libjpeg. Let's first look at line 10. A function pointer is stored into the progress struct. In line 11, we store a constant to the next field of the struct. That constant is in the valid range of code addresses. In fact, it may be the exact same value as the address of callback func. There is statically no way to tell from this binary which of those fields is an address and which is a constant. Mixema, which in this case inherits its analysis from IDAPRO, incorrectly rewrites this code because it guesses both fields of the struct are code pointers and rewrites them. In BinRec, we observe the use of progress monitor as a code pointer and therefore do not need to rewrite pass limit. Indirect control flows go to destinations computed at runtime. Static binary analysis must use heuristics with something like value set analysis to over-approximate what set of targets are valid for each control flow. With dynamic analysis, we can instead directly record the exact targets of each indirect control flow transfer. If there is a return instruction in a binary, we will directly observe where it returns to. We represent this control flow in the lifted LLVM-IR as a switch statement where the cases are the observed targets. An additional challenge for static rewriters is handling external entry points. Every binary analysis has a region under analysis and a region outside analysis. A good example to illustrate this scenario is a callback. Our program to be rewritten calls a quicksort function in a library outside the analysis region. It passes the library a pointer to our compare function, which the library invokes. If you don't do anything, quicksort in the library will invoke the original compare function pointer. But your compare function doesn't exist there anymore, so you'll get a segfault. You need to somehow make sure the rewritten version of your compare function gets invoked. Static rewriting approaches have tried the following three approaches, each of which has a limitation. Option 1 is to consider all libraries as part of your analysis and rewrite them. This effectively statically links them into your rewritten program and blows up the system memory usage. Option 2 is to rewrite code pointers. But as we saw in the libjpeg example, this is an unsolvable problem. They can use heuristics or only implement support for a limited set of well-known libraries. The third possibility is to add a layer of indirection to every indirect control flow in the program and create a giant lookup table. That works, but it's unnecessarily slow. In BinRec, we use dynamic information to create a sound and performance solution to the external entry point challenge. We do not patch any code pointers. The library calls to the original callback address. We install a trampoline at the original callback address and use it to jump to the rewritten version of that functionality. Because we know exactly which functions will be accessed externally, we only install trampolines there. This allows for optimization by restricting the number of entry points to rewritten code and therefore allows variables to live in registers where they previously required stores. We've been able to solve many of the difficult problems in static binary rewriting by using dynamic analysis. But dynamic analysis brings its own set of challenges. The principal of them is achieving coverage through program paths of interest. In our dynamic lifting engine, we try to efficiently cover as many paths as possible. We install configurable handlers that provide options if a path is missing. We run many executions of an input binary in parallel in our lifting engine. We can use explicit test cases, fuzzed inputs, and since we are built upon S2E, concolic execution to drive new paths through functionality of interest. Next, we merge all the collected dynamic traces into one control flow graph. We deduplicate paths to avoid a code size explosion. We have 4 possible handlers which we can install, which will be invoked whenever a path is missing. The path miss handler can be optimized out when users have high confidence they have exercised all functionality of interest. We can log the path miss and abort execution, which is ideal when newly reached code paths are assigned a malicious input. If the original binary is rewritten to the same architecture, then we can use a fallback handler to execute the original binary whenever there is a path miss. Finally, we could use incremental lifting. Incremental lifting uses a path miss as a starting point to begin another trace. We begin tracing at the miss point, which avoids the need to re-execute the entire program from the entry point. The new trace can be combined with all the existing traces to produce a new version of the rewritten binary. Incremental lifting can be combined with the fallback handler so the first version of a binary can continue executing while the new version is being produced offline. Here's what it looks like to incrementally lift the bzip2 benchmark. We initially lifted bzip using only the training inputs from the benchmark suite. We then ran the reference inputs with the incremental lifting handler. Each triangle is one path miss from which we have lifted additional program paths. At the rightmost point in the graph, we have produced a rewritten binary which can handle all of the spec workloads. Now we come to what I think is the most important result in this paper. BinRec correctly recompiles the entire spec integer benchmark suite, and the rewritten binaries have good performance. For already optimized binaries, the process of rewriting causes 29% overhead. For unoptimized inputs, we increase their performance by, on average, 2%. For comparison, we look at the reported performance of static rewriters. They come with their own limitations and optimizations, so I encourage you to refer to the source papers. We also collected performance data for those benchmarks that Mixema correctly recompiled. Unfortunately, Mixema does not publish any of their own performance data. Across the board, BinRec outperforms these approaches. The price we have to pay to use dynamic analysis is in time to lift a binary. BinRec takes approximately 450 times longer to lift spec than Mixema. This of course depends on the workload, is a one-time cost, and we did not attempt to optimize the lifting time. We've done the hard work of lifting a binary into LLVMIR with dynamic analysis. We've also made it possible for lifted binaries to use whatever dynamic link libraries you would like. It was all worth it because now we can use off-the-shelf compiler transformations on binaries. I've only time to discuss two today, so please take a look at the paper for more. We retrofitted lifted binaries with address sanitizer. In brief, ASAN finds spatial and temporal memory access violations. It instruments all memory accesses to check if you're accessing a red zone, i.e. there is a violation. ASAN works off the shelf with no modifications on binaries lifted with BinRec. All memory accesses in the program are instrumented. All of the heap allocations are instrumented. One limitation is that no stack allocations will be instrumented, and that is because we can't discern which stack slots belong to which variables in the lifted programs. Please refer to a paper for more discussion on that issue. We took programs with memory use bugs, lifted them with BinRec, applied ASAN, and then when we tested them, ASAN reported the violations. Tail calls, multi-entry functions, and overlapping instructions are hard to analyze statically. This problem can become worse if the author of the code intentionally obfuscates the logic of the application with unaligned accesses, virtualization, packing, or encryption. Since BinRec uses dynamic analysis, we can bypass them. We record the actual instructions executed by the CPU, not what is present in the file. Our representation of lifted programs has the original code semantics present in the clear without the packing or encryption. To remove virtualization obfuscation, we instrument the binary with BinRec and execute it again to record the control flow graph. Please see our paper for details. We automatically retrofit all programs rewritten with BinRec with control flow integrity. We use the dynamic traces to determine our CFI policy. If a control flow edge was taken in the traces, it is allowed. One trade-off we make to increase performance is to merge calling contexts. Therefore, if we saw the circled traces on the right, both E and F would be valid successors of node D. We enforce our policy by making all control flows in the recovered binary direct. There is a switch table for each control flow transfer in the original binary that enumerates all of the allowed targets. BinCFI is a popular CFI implementation that works on stripped binaries and uses static analysis. They use a heuristic which allows indirect calls to go to any function with its address taken, because that is one of the only sound choices you can make based on the limited information available in static binary analysis. BinRec is on average 25 times more restrictive than BinCFI. By being more precise, we make it more difficult for attackers to construct a code reuse exploit. Now I would like to conclude. We created a first-of-its-kind framework to use dynamic analysis to lift binaries into LLVMIR and recompile them. The approach is free of heuristics and supports a large variety of input binaries, including obfuscated ones. BinRec enables off-the-shelf compiler transformations to be retrofitted to binaries. And finally, it produces rewritten binaries with low overhead. BinRec, dynamic binary lifting and recompilation.